Okay, good morning. Let's continue. So this will be our last class on descriptive statistics. Um, that means we'll soon migrate into the topic of inferential statistics, which is presumably even more fun. Okay, but let's finish up, with the z-score, which is very important. Okay, so previously we talked about normal distributions. And we talked about, how we can sort of make sense or start to make sense of the normal distribution with, concrete values. So imagine, we have a sample of participants. Where's my pen? Okay, so imagine we have a sample of participants, and each one of them answered a questionnaire that contains a 7-point scale, right, from strongly disagree to seven very strongly agree with a certain issue. So that means very likely we'll have all these possible outcomes, right? So one, two, three, four, five, six, seven. There are the possible outcomes of this particular variable. So what we can do is we can sort of plot this distribution, right? How these different outcomes of the variable are distributed across the sample of participants, right? So here we assume that the distribution follows a normal distribution that's very beautifully curved, right? It's bell-shaped, perfectly symmetrical, more values clustered around the center, fewer values or more extreme values at the tails, right? So this is a tail, this is a tail. On the y-axis, we have p parentheses x. Um, this simply means the probability, right? So the y-axis plots the probability of observing a particular outcome, 2 or 3, or any other value as we'll see in a minute, right? So the probability of observing a particular value within the range, of course, right, from 1 to 7, from the sample of participants. So if the distribution or these values are normally distributed for this particular sample, can we find a way to figure out more or less exactly the probability of observing, let's say, a 4, right? So let me repeat, if we know that these values, right, from 1 to 7, they are normally distributed, that is, their distribution follows a normal distribution for this particular sample of participants. Right? We can imagine we stack all those individuals, right above all these values, right? So here is one participant, another participant, all the way up, right? Here is one participant, a second participant, all the way up, right? So that's how we sort of came up with this curve, right? So we assume that as we stack all those participants scoring different values, we sort of have this kind of shape, right? It's like, these guys, they score 3, and this the last person who scored 3, right? So obviously we can sort of imagine that we can see actually, right? So with this distribution, there are more people scoring 4 than more people scoring 1, and there are more people scoring 3 than people scoring 1, but there are less people scoring 3 than those who score 4, etc. Okay, so that's what this distribution means, right? How many people under the curve scoring all these possible outcomes of the variable. Okay, so now if this if this is our distribution, is there a way to find out the probability, right? The probability of people who scored a particular value, say 4, right? Well, you can say, well, Andrew, why do we bother? Because we can count, right? The problem is, of course, if you only survey 20 people, or if you survey even 200 people, right? You can count. But imagine that you're working for Google or Facebook or whatever company, right, or the even the Hawaii First Bank, where the data sets are measured in gigabytes. That is, you have thousands, millions of thousands, hundreds of millions, whatever, large number of people. So with that, you cannot simply count, right? It would take you years to count the number of people who, for example, clicked on a certain YouTube clip 5 times, right? So that's when this kind of distribution comes in handy. Once we sort of know once we ask computers to plot all those data, then by looking at this distribution, we actually, well, statisticians actually have figured out a way of inferring the probability of observing all these kinds of values, right? Provided that these values are normally distributed. Okay, so let's do that. Let's try to sort of understand this process. Okay, so our question is, I believe the question that we ended the previous class with is, if we're interested in this particular value, and if we would like to know how many people, right, or the probability of observing a value of 4, provided that these values of this variable are normally distributed, how can we do that? Well, it seems pretty straightforward, right? You say, if this y-axis plots the distribution or the probability, then what we can do is we'll first draw a line, right? A vertical line so that it would touch 4 at this end, and it would it will intersect with this curve at the other end. And right at the point of intersection, we draw a horizontal line, right, parallel to the x-axis, and make this line to intersect with the y-axis. And this intersection point will be, or should be, the probability of observing 4. So if we sort of say, well, here is about 1, then by eyeballing, it will say, here is about 0.8. Well, not precise, but definitely between 0.7 and 0.9, so we'll say it's 0.8. So you will say, aha, the probability given this distribution of observing 4, right, is about 0.8. Wrong. Okay. This is the wrong way of figuring out the probability of observing a particular value from not just normal distribution, but any continuous distribution, right? This is a continuous distribution. It's not a bar chart, right? So we assume that these values are continuous. Then you may ask, oh, then what is the correct answer, right? It's not about, the precision of eyeballing. I'm not saying that it's not 0.08, rather it's 78, right? That's not about the precision. It's not a matter of precision, but this method, this way of finding out probabilities under a continuous distribution is fundamentally incorrect, right? So the correct answer for this question is actually 0, or technically almost 0, infinitely close to 0, right? That's the answer. You may say, well, how come? It can be because you might say that, a very large value is close to 0, probably finding a very large or very small value 0. There's no way that, finding a value of 4 is 0, because you do have a height, right? You do have a difference, for example, between this point and this point, right? It can be. Well, it actually is. It actually is, right? Here's, a little bit of counterintuitive, and hopefully I can explain this to you with a non-mathematical method. Okay, but first of all, let's sort of accept this conclusion. That is, with a normal distribution, right? This is a normal distribution. With a normal distribution of a truly continuous variable. So here we're assuming that these 7 points form a continuous sort of scale, right? But when we say a truly continuous variable, um, what are some examples that come to mind? We can have time, right? That's a truly continuous variable. Well, I mean, we can of course chop time up into days and weeks, but technically it's flowing, right? So this particular moment is definitely moving, right? In a very continuous sense from the previous moment. Or temperature, that's definitely a continuous variable. And there are many other examples, right? Age, for example, money, right? Income, for example, right? Height, weight, right? So those, with a truly normal, with a truly continuous variable, and if this variable is normally distributed, then the probability of observing an exact value, for example, 4 precisely, right, is very, very, very small. So small that we can regard it as 0. Okay? So here's why. So, if you understand integrals and differentials, you will very soon to see the reason why. But I assume that most of us here are not very familiar with integrals and differentials, so that's why I used a non-mathematical explanation, trying to make sense of this particular conclusion, right? So imagine that we're measuring the volume of rainfall in this particular city, or monthly volume, okay? So immediately you will see that the volume of rainfall is a truly continuous variable, right? It's measured in, I don't know, square inch, for example, right? And that is a continuous variable without any dispute. So and from public data, I sort of gathered these two numbers, the range, right? The average monthly volume of rainfall in Honolulu is from 0.11 to 16.9 inches. I should say cubic inches, right? According to public data. But anyway, right? This is just to illustrate that it is a truly continuous variable. Um, Now let's say, I don't even have to assume that the volume, right, of rainfall follows a normal distribution. That doesn't matter actually. As I said actually, the rule that we just said, right, the probability of obtaining a precise value is very close to 0 actually applies beyond normal distributions. It applies to all kinds of continuous distributions, Poisson distributions, t distributions, f distributions, chi-square distributions, whatever, right? As long as a continuous distribution. But anyway, okay. So that's why I didn't say that we assume that it's a normal or a distribution or other kinds of distribution. But my question here is because our focus is to find out or is to reason through why the probability of obtaining a precise value from a continuous variable is close to 0. So here the question is, what is the chance of obtaining exactly 5 inches of rainfall, right? So note, exactly 5, right? That means I'm not saying that I want to know the probability of observing 4.999999 inches or 5.00001 inches, right? I want exactly 5 inches, right? I want to know the probability of observing 5 exact inches. If your boss gives you this task, right, to measure 5 inches of rainfall exactly, not 4.9999 nor 5.0001, your boss has given you a mission impossible, right? Because we know that given our, measurement, or the typical way that we measure stuff, it's practically impossible to obtain an exact amount of volume or length or weight or whatever property that they can think of, and not, you know, 1 unit more or 1 unit less. Okay, so that means the probability of observing an exact value is very, very small, extremely small, so small that we can comfortably assume that it is zero. Okay, so that is why, as we said, given a truly continuous variable, right, the probability of observing an exact value is also close to zero, right? Because we cannot even obtain a exact value from a sample or probability distribution, then the probability of observing it by extension, by logical extension, right, is also going to be very, very small. Okay, so I hope this makes sense, and can convince you that the probability of observing an exact value from a continuous distribution is close to zero. Okay, but having said that, right, still we would like to know what's the probability of finding a given value, because that still will give us information, very useful information. Um, it's just that, the previous example only says it is not correct, right? It is not correct to find out the probability of a particular value using this kind of method, right? So that suggests the height, right? The height of a curve um, is actually not the probability of observing a particular value here, right? The value x. So the height of the distribution actually is not what we should be looking for. But then you may ask, well, then what should we be looking for, right? So given that it is very difficult to obtain exactly 5 or an exact value, right? It can be anything. It can be 4, it can be 3. So given that it is very difficult to find a probability of finding of a exact value, what we can do then is we relax our requirement and say it's okay that you include some errors there, right? Recall we do talk about measurement errors, right? So anything that's not precise will be considered as error, right? So we're saying here, well, if it is impossible to observe the probability value for an exact value, um, then let's observe the probability or find a probability for a very, very narrow range that contains the value that we're interested in. So here 5, right, is slightly larger than 4.9999, and 5 is slightly smaller than 5.1111. So this range, right, so close, but containing 5, right, can be roughly considered as the probability of observing 5, this particular value. Okay, for the same idea, right, if you want to say, well, what is the probability of observing 4 from a continuous distribution, then what you can do is, instead of finding the probability or p-value for 4 exactly, you can say, well, what's the probability of observing a range of value, right, or an interval of values ranging from 3.9999 to 4.00001. Okay, a very small interval that contains the target value. This, right, finding the probability of this interval is mathematical possible, and there's readily ways to do that. All right. So to sort of recap the point and graphically sort of present our previous argument, right? Given this normal distribution, given these are the possible values that are observed from this variable, and and on the y-axis we have the probability level, right? So our question is, what is the probability of observing a precise value? Okay, so instead of using, the height method, right? So instead of saying, what's the height of this point, we're looking at, first of all, a method where we'll determine a very small range or band that includes our target value. Okay, well, here is not very narrow, but for illustration purposes, let's say this is a very narrow band that includes 4. Okay, and then the next step, actually, to find out the probability of observing a value 4 is to calculate the area of the band under the normal curve, is to mathematically find out what is the area of the shaded part, right, between the curve and the x-axis, and also within the two boundaries, right? Here's one boundary, here's the second boundary. So what is the area of this shaded part? And the area of the shaded part will be the probability of finding 4, right? Or technically, finding the very narrow band that contains 4. Okay, and the probability is the area of the shaded part. Okay, so this is a little counterintuitive, but for now, let's remember this sort of conclusion. So to go back to our example, right? So then under this distribution, or any continuous distribution, right, the probability of observing 4 is made to equal the probability of finding any value that's within this very, very small range, right? So it could be 3.99999 or 3.0005, right? That's okay. We'll consider the probability of observing 4.00005 equivalent, right, enough to the probability of observing 4. Okay? So that gives us actually a way to do more than finding out the probability of identifying one single value. So now we can actually say, well, then can we do the same thing to find out the probability of observing a value that's larger than 4 but smaller than 5? Well, of course, right? Because just now we saw that the way of finding the probability of observing a particular value is by specifying a very narrow interval that contains the target value. Then of course we can find out the probability for observing any value that's within an interval. Easy enough. We'll put a boundary at 4, we'll put a boundary at 5. So as long as we can calculate, which we can, the area of this part, right, the shaded area, the shaded part, right, the area of the shaded part, that will give us the probability of observing any value that's larger than 4 and smaller than 5, right? So the area of this part, the shaded part, will be the probability of observing any value, right, any x that's larger than 4 but smaller than 5 within here. Okay, so that's the probability. Okay, now let me ask you, given this distribution, then what's the probability of observing a value that's larger than 5 here or smaller than 4? How can we do that? What's the probability of finding a value from this sample, right, given this distribution that is larger than 5 or equal to 5 or smaller, or no greater than 4? Okay? It's actually very easy, right? You should pause now and think about it before I announce the answer. The answer is the probability of finding a value that's no smaller than 5 or no larger than 4 will be the difference between 1 minus the probability of finding any value that's within this interval. Okay? It makes sense, I hope, to you very quickly that why we need to use why we can subtract this probability from 1, because we said in the previous class that the total area under this curve, right? The total area under this curve is 1, because the total area under this curve represents the probability of observing all possible values of this variable. Then the probability of observing all values of variable, well, that's certainty, right? So certainty, mathematically, it's 1. So in other words, the total area under this curve is 1, and if we already know the shaded part, the area of the shaded part is this, then of course the area left, right, from left within this curve, right, from this shaded part will be 1 minus the probability of observing any value that's larger than 4 and smaller than 5, right? So it will be this part, right? It will be the area under the curve bar the area of this part. Then of course, right, we use subtraction. Well, similarly, right, we can calculate the probability of observing a value that's greater than a particular value. What should it be, right? So that's a range. That's also interval. That means, from 4 to all the way to 7, actually, right? Because 7 is our upper bound, right? But we don't have to specify 7 here because, this curve will only extend to 7, right? Well, it's not precise here, but you can imagine there should be a cutoff line here, right? The curve should be like this, right? Ends at 7. Okay? So then, right, what we also need is an interval, right? So it turns out that 4 is the mean here. That is, it will, if we impose a center line, it will run through 4. Okay? So in other words, to find out the probability of observing a value that's greater than 4 is just to find out the area of this part, right? From 4 all the way to 7. Okay? So it will be actually 0.5 because this is actually half of this bell-shaped curve, right? So if the total area under this curve is 1, and if 4 happens to be the mean, right, then of course, if we impose a center line, that would divide this curve into 2 halves. And of course, right, then it will be 0.5, right, as the chance of observing any value that's greater than 4. Okay, so here is, P. The probability of observing any value that's greater than 4 is 0.5, provided that these values are normally distributed and 4 is the mean, right? It's also the median, it's also the mode. Okay? Well, 0.5 will also be the probability of observing a value that's smaller or no greater than 4, right? Because that's 1 minus 0.5, that gives you 0.5. Okay? So the essence, in other words, in more general terms, of finding, any particular value, any, an interval of values under a normal distribution or any continuous distribution is to specify a relevant, interval, right? If we are looking for the probability of finding a particular value, an exact value, then we specify a very narrow band across it, that contains it, and our job then is to, figure out, or here, right? So let's say 3 is here. Then our, to find out the probability of observing 3 under this distribution, then we just, specify a very narrow band that will contain 3, and then we'll calculate the area, right, of this band. So the area of this band will be roughly the probability of observing 3. But if you want to say, well, what's the probability of observing any value that's larger than 1, smaller than 2? Easy, right? It will be the probability, it will be actually the area of this part, right? Then you say, well, what's the probability of any value that's greater than 2, right? Then it will be all the way, right? The area of the part, to the right of 2, and the probability of any value that's smaller than 2 will be the area of the part that's to the left of 2. Okay, easy enough, I hope. Okay, so far we have actually sort of worked out the general principle or general way of finding out probabilities of observing some kind of value if the value follows a normal distribution. Mathematically, there are many ways to do that, but for the purpose of this class, we'll be focusing on what we call the empirical rule. Empirical rule is a approximate way of finding out probabilities. The probabilities that obtained from using the empirical rule will not be precise or exact, but it's close enough, right? And for this introductory class, we consider the empirical rule a good enough method of working out the probability of finding or observing some kind of value if the values follow a normal distribution. Okay, so here is the empirical rule, what the rule says. The first statement of the empirical rule says, given a normal distribution, okay, so there will, the probability of a score that falls within one standard deviation around the mean, right? Here is one standard deviation above the mean. Here's one standard deviation below the mean, right? So it says the probability of any value that falls within this range is about 68%, or the probability is 0.68, or the area, right, of this shaded part bound by one standard deviation above and below the mean is 0.06. Okay, that is, for any value that's larger than or smaller than one standard deviation around the mean will be 0.68, right? Okay, the second statement of the empirical rule says, for any value that falls between two standard deviation below or above the mean, right? Any value that's within this interval, right, is about 0.95, right? That is, there are 95% of the chance that we can observe a score that will fall within this interval, okay? 2 standard deviation around the mean. So any value, right, that's greater than 2 standard deviation below the mean or smaller than 2 standard deviation above the mean, the probability of observing this value is 0.95. Lastly, it says, the empirical rule says, for any value that's within 3 standard deviation around the mean, the probability of observing this value is close to, but not yet 1, right? It's 0.99. That simply means almost all values, right, will fall within 3 standard deviation below and above the mean. There are a few values that are not included, but the majority of values will be within 3 standard deviation above and below the mean. Okay, so we have, in other words, 99% of the chance to observe a score given this distribution, right, that's larger than 3 standard deviation below the mean and greater than 3 standard deviation above the mean. Sorry, it should be 3. Okay. it should be 3. Okay, right? Exactly. Okay, so this is the 3 statements will constitute what we call the empirical rule. Okay, but then how do we use it? So imagine, right? Angie surveyed 500 people on their attitudes toward gun control on a 7-point scale, right? And then we know from calculating, from working with the numbers, uh, that these 500 people, the average score of these 500 people is 4, and the standard deviation of this sample value is 0.5, right? We further assume that the scores, these 500 scores, follow a normal distribution. I can ask about how many people in the sample had an attitude score that's greater than 3.5 and smaller than 4.5. Okay, so given all these sort of conditions, we can roughly plot the distribution, right? First of all, it's normal, okay, and then we know that the mean is about 4, and standard deviation is 0.5, right? And then we want to know about how many people in the sample had an attitude, or scored, about how many people in the sample scored between 3.5 and 4.5. So first of all, we should find out where are 3.5 and 4.5 on this distribution. That is our first step. We should establish the cutoff values, because the cutoff values will allow us to establish boundaries, right? To determine, to help us determine the area of a shaded part, but then we need boundaries to first of all specify the part whose area we want to find out. Okay, so that translates to the question of where are 3.5 and 4.5 on this distribution, or on this axis, right? This axis represents values, right, of the variable. Okay, what do you think? Where should they be? Okay, to find out where they are, well, actually, you should already see that 3.5 should be around here, right? And 4.5 should be around here. Okay, but to be more precise, we will need to calculate their z scores. The z values corresponding to 3.5 and 4.5. Okay, should be easy, right? If we recall, z values equals to the target value minus the mean divided by standard deviation. Okay, so for 3.5, we know that it's the mean of 3.5, or the sample from which 3.5 is drawn, is 4. Okay, and then we divided this difference by standard deviation, which is 0.5. Okay, so it's negative 0.5 divided by 0.5, so that's negative 1. Okay, and we calculate the second sort of z value, that will be 4.5, right, minus 4 divided by 4.5, so that will be 0.5 divided by 0.5, that's exactly 1. So that means 3.5 is exactly 1 standard deviation below the mean, and 4.5 is exactly 1 standard deviation above the mean, right? Because the difference here is 0.5, and exactly 1 standard deviation. The difference here is 0.5, which is also exactly 1 standard deviation. So 3.5, 4.5 are exactly 1 standard deviation below and above the mean. So this will be the part whose area we're going to find out. And by finding out the area of this shaded part, we should be able to know the probability of observing any value that's within this interval, right? So the last step, once we figure out, the number of standard deviations that these values are around the mean, we will be able to apply the empirical rule, okay? Because we just said, right, the first statement of the empirical rule says there will be about 68% of values that will fall between 1 standard deviation above around the mean, okay? So this is it. We know that from calculation that 3.5 and 4.5 are exactly 1 standard deviation around the mean. And according to empirical rule, there should be 68% of the scores that will fall within this interval. So it will be 0.68 times 500. That will be 500 times 0.68, that's 340. So there will be 340 people who will score between 3.5 and 4.5. Isn't that cool? Okay. Let's look at more examples. Of course, some of you might be confused. This is our first question. The second question, how about, how many people in the sample would score between 3 and 5 instead of 3.5 and 4.5? Okay, so you should pause right now and try to solve this question for yourself, right? Before hearing my answers. But let's work out this question together. So again, the first step is to establish the cutoff values, right? Because given this normal distribution, right, we want to find, and this is the mean, right? We want to find out, where is the part, that represents the area of the part that represents this particular interval, right? So roughly we can eyeball that 3 might be here, 5 might be here, but we don't know exactly, right? What's the relationship between 3 and 5 to 4? Okay, so that's why we need to calculate z-scores. So the z-score for 3 is 3 minus 4 divided by 0.5. That will be negative 1 divided by 0.5. So that's negative 2. That means 3 is 2 standard deviation below the mean. Okay, then what about the value or 5, the z value of 5? So it will be 5 minus 4, right? Here's the mean, right? Divided by 0.05. So it will be 1 divided by 0.05. It will be 2. That means 5 will be 2 standard deviation above the mean 4. Okay, it makes sense because, the distance between 4 and 5 is 1, right? And 1 will be 2 standard deviations because 1 standard deviation is 0.5, then 2 standard deviations will be 1. Okay, same here. The difference between 3 and 4 is 1, and 1 is exactly 2 standard deviations. Okay, and the third step is to apply the empirical rule. We know from the empirical rule, the second statement of the rule, that says the probability for any value that falls between 2 standard deviation around the mean is exactly 0.95. right? So that's why we use 0.95 to multiply 0.95 with 500. What's that? That will give us 475. There we go. So the answer to this question is there will be about 475 people that will score between 3 and 5 given this normal distribution. Okay? What about between, I'm sorry, between 2.5 and 5.5? How many people in the sample would have an attitude score between 2.5 and 5.5? Right? Easy. Again, right, this is our distribution. We know this is 4, the mean, and we need to find out, where exactly are the cutoff lines determined by 2.5 and 5.5. So 2.5 would say will be around here, right? Just to eyeball it. And 5.5 will be around here, just eyeball it. But we need exact values, right? The exact values will be given by the z-score. So the z-score for 2.5 will be 2.5 minus 4, right? Divided by 0.5. So here is negative 1.5 divided by 0.5. So that's negative 3. That means 2.5 will be 3 standard deviation below the mean. What about 5.5? Right? So 5.5 divided minus 4 divided by 0.5, that's 3. So that means 5.5 is exactly 3 standard deviation above the mean. So that makes sense. 5.5 minus 4, that's 1.5. And 1.5 is exactly 3 times 0.5. So 5.5 is exactly 3 standard deviations above the mean. And 2.5 is 3 standard deviation below the mean, because the difference between 2.5 and 4 is 1.5. And 1.5 equals to 0.5 times 3. Okay? So, and then we can apply the empirical rule. The third statement of the empirical rule says, for any value that falls within 3 standard deviation around the mean, right? That's 3 standard deviation around the mean, below and above the mean, right? Is 0.99. So that's why we use 0.99 to multiply with 500 people. So the answer is 495. So there will be about 495 people scoring between 2.5 and 5.5 given this distribution. Right? That's almost all 500 people, right? There are only 5 of those people who had scores that's more extreme than 2.5 and 5.5. Make sense? I hope so. Okay. We can do more. How about we find out the number of people who scored between 3 and 4.5? Now, you should be rather familiar with the procedure, right? So we're saying, okay, so here's the distribution, right? And the mean is 4, standard deviation is 0.5. So we say, well, where's 3? 3 is about here, okay? And if 3 is here, then 4.5 is about here. So it looks like this will be the boundaries, right? And it looks like this will be, the area that represents the probability of finding any value that's greater than 3 but smaller than 4.5. Okay? But now, in order to apply the empirical rule, we need to know the exact, difference between 3 and 4, and the exact difference between 4.5 and 4 in terms of standard deviations, because the empirical rule says it's all about, 0.68% is within one standard deviation around the mean, right? We need to know how many, in other words, how many standard deviations are 3 away from 4, and how many standard deviations is 4.5 away from 4. Okay, so that's why we need to calculate z-scores, because z-scores represents the number of standard deviations of a value relative to its mean. Okay, so the z-value of 3, easy, 3 minus 4 divided by 0.5. That will give us -1 divided by 0.5. That's -2. So that means 3 is about 2 standard deviation below the mean. Okay? Then what about 4.5? So 4.5 minus 4 divided by 0.5. That's so 4. That's 0.5. Sorry, 0.5 divided by 0.5. That's 1. So that means 4.5 is exactly 1 standard deviation above the mean. Okay? Yeah, so 1 standard deviation above the mean, but here are 2 standard deviation below the mean. Wait a minute, we don't have any statement in the empirical rule that says that, because all we have is, well, there will be, the probability is about 0.68 to find any value that's, between 1 standard deviation around the mean, and we also have, you know, um, for any value that's within 2 standard deviation around the mean, the probability of finding that value is 0.95. We don't have anything that's asymmetrical. That's 1 standard deviation above the mean, whereas 2 standard deviation below the mean. What do we do? Okay. All right, so the way to figure out this particular probability will be to rely on the fact that this probability distribution, this normal distribution, is perfectly symmetrical. Okay, so I'm going to erase all. So this is a symmetrical normal distribution. And from the first empirical rule, we know that the probability is about 0.68 to observe any value that's 1 standard deviation above and below the mean. Okay, so it's 1 standard deviation. So here's the mean, is minus 1 standard deviation, and okay. So in other words, the total area of the shaded part here is 0.68. Right? That's the empirical rule, right? About the probability is 1.68 to observe any value that's within 1 standard deviation around the mean. Okay, so if this normal distribution is symmetrical around the center line, that is around the mean, what is the distribution, sorry, what is the area of this part? That is just between the mean and 1 standard deviation above it. If the entire area is 0.68, then what is half of it, in other words? Because this part, the shaded part, is also symmetrical around the mean. Okay, so we divide it by 2. That will be 0.34. So in other words, to observe the probability of observing any value that's greater than the mean but smaller than 1 standard deviation above the mean, so within this interval, is about 0.34. Okay, and then we can similarly find out, in other words, right, what's the probability of observing any value that's between the mean and two standard deviation below the mean, this part. Okay, because according to the empirical rule, right, sorry, 95, the probability of observing any score that's within two standard deviation above or below the mean is 0.95. Then now we only want the probability of observing any score that's greater than two standard deviation below the mean but smaller than the mean. That is half of 0.95. So half of 0.95 is 0.475. So the area of this part is 0.75. Now we can figure out, right? So what's the probability of observing any score that's one standard deviation above the mean, but two standard deviation below the mean? So it will be 0.475 plus 0.34, right? So 0.475 plus 0.34, that will give us 511. So the probability, in other words, of finding any score that's above two standard deviation below the mean and below one standard deviation above the mean, that is this part, is 0.815. So the number of people who will score between 3 and 4.5, because 3 is here, right? 3 is two standard deviation below the mean, which is 4, and 4.5 is one standard deviation above 4, which is the mean. So the number of people who scored above 3 and below 4.5 will be 500 times 0.815. That will be 500 times 0.815. It will be 407.5. Well, it will be around 408, right? So about these many people will be scoring between 3 and 4.5, right? So this is how we solve this problem. Very lastly, we can also ask, what about the number of people who scored below 2.5 but greater than 4.5? How do we solve that, right? So easy, right? So again, we need to determine where's the interval. So here's 4 and here is 4.5, right? So that's, we know, is exactly one standard deviation above 4. But where's 2.5? 2.5 is here, right? We know 2.5 will be exactly 3 standard deviation below the mean, right? So 2.5 minus 4 divided by 0.5, that's negative 1.5 divided by 0.5, it will be negative 3, right? So 2.5 is exactly 3 standard deviation below the mean. So this part would then be the probability of observing any value that's greater than 2.5 but smaller than 4.5. But wait a minute, this is not what we want. We want any value that's smaller than 2.5 but greater than 4.5. But solving this is easy once we can understand, or once we can figure out the probability of observing any score that falls in this interval. Because now our target probability, right? Our target probability, that's probability of observing x that's smaller than 2.5, and right, or at the same time, um, larger than 4.5 will exactly be 1 minus the probability of observing any score that's greater than 2.5 but smaller than 4.5. Because this part adds this part adds this part must equal to 1. Now we know the area of this part is this expression. Now what's the sum of these two parts? Well, it'll be 1 minus the area of this part. Okay? So now the question becomes, how do we figure out the area of this part? Easy. Okay? You should know by now. This is 4. We know 4.5 is exactly 1 standard deviation above the mean. Okay? So that means, right, the area of this part will be 0.68 divided by 2. That's 0.34. Because 0.68 is the probability of observing any value that's 1 standard deviation above and below the mean. Now we only want above, right? So that will be 68 divided by 2. Now 2.5 we know is 3 standard deviation below the mean. And we know from the empirical rule that the probability is 0.99 for any value that's within 3 standard deviation around the mean. Now we only want below, right? We don't want anything that's above, because we only care about values that's within this interval. So it will be 0.99 divided by 2. Okay, so the probability of observing any score that's greater than 2.5 but smaller than 4.5 will be 299 plus 0.68 divided by 2, right? So it will be 0.99 plus 0.68 divided by 2. It will be 0.835. This is the probability of observing any score that's greater than 2.5 but smaller than 4.5. But our goal is to find out the value that's smaller than 2.5 or greater than 4.5. As we said just now, right, then this probability is very easy. So for any score that's smaller than 2.5 or greater than 4.5 will be 1 minus the probability of any value that's greater than 2.5 but smaller than 4.5. Then it will be 1 minus 0.83.5. Sorry, 1 minus 0.835. That will be 0.165. Okay, so the number of people who scored number of people who scored below 2.5 but above 4.5 will be 500 times 0.165 82.5. So about 83 people from this sample of 500 people would score below 2.5 or greater than 4.5. Okay, So this is how we use or make use of empirical rule, right, to describe the sample. Isn't it very useful and cool? Okay, so I know these could be overwhelming for some of you. So all I'm asking you is to, well, listen to this part again and again, right? Because I have provided all the answers and procedures of figuring out all these questions. So all you need to do is to listen to this part again and again till you understand why we're doing this. Okay? And of course, if you still are confused, don't hesitate to email me, and we can meet face to face to go through the questions. Okay? So I will soon post question homework assignment, I believe number 4, which will be due on Wednesday, I believe. Okay, I will see you tomorrow.